Module 14, routing concepts. So it's basically explain how routers use information in packets to make forwarding decisions. And so it's how routing works. So we're going to look at path determination. So basically, how does a router pick the best path to get towards a destination? And then packet forwarding is explain how routers forward packets to the destination. Then basic router configuration. That's just a bit of a rehash on what we've done before. Then the IP routing table, we'll look at how a routing table is structured. And then static and dynamic routing, we'll compare static and dynamic routing concepts. So it's more background knowledge in this chapter, and then we'll actually go on and how to do some routing later on. Okay, so path determination. When a router receives a packet on one interface, it determines which interface to use to forward the packet to the destination. This is known as routing. So the interface that the router uses to forward the packet may be the final destination, or it might be a network connected to another router that is used to reach the destination network. Each network that a router connects to typically requires a separate interface, but this may not always be the case. The primary functions of a router are to determine the best path to forward packets based on the information in its routing table and forward packets towards their destination. Okay, so the router uses its IP routing table to determine which path or route to use to forward a packet. And so in this diagram, we've got router 1 and we've got router 2, and they've each got a LAN directly connected. And so the router 1 and 2 will use their respective IP routing tables to best determine the best path and then forward the packet along that path. So the best path in the routing table is known as the longest match. Now we're talking about the subnet mask or prefix length there. So the routing table contains route entries consisting of a prefix, so network address and its length, and prefix length. For there to be a match between the destination IP address of a packet and a route in the routing table, a minimum number of far left bits must match between the IP address of the packet and the route in the routing table. The prefix length of the route in the routing table is used to determine the minimum number of far left bits that must match. The longest match is the route in the routing table that is the greatest number of far left matching bits with the destination IP address of the packet. The longest match is always the preferred route. Note the term prefix length will be used to refer to the network portion of both IPv4 and IPv6 addresses. In the table below, an IP packet is a destination address of 172.16.0.10. The router has 3 route entries in its routing table that match this packet. And so they are 172.12.00/12. Another one is /18 and another one is /26. Of these 3 routes, 172.16/26 has the longest match and will be chosen to forward the packet. For any of these routes to be considered a match, there must be at least the number of matching bits indicated by the subnet mask of the route. And so here, basically, as you can see, it just counts, because it's got a prefix length of 12, that's how much of a match we're talking about. And so, of course, the 18 and then the 26, of course, is by far the longest. So an IPv6 packet has a destination IPv6 address of X. This example shows 3 route entries, but only 2 of them are a valid match, with one of those being the longest match. The first 2 route entries have prefix lengths that have the required number of matching bits as indicated by the prefix length. The third route is not a match because its /64 prefix requires 64 matching bits. And so we've got this network number we're trying to match. And so 16, 32, 48 bits is what we've got here. Or suppose we could subtract the zeros off the end as well, but that's how many we've got here. And so that's why that 64 is not does not match, because it's got a different number there. And so it becomes not a match. So that's why we've got the 40 and the 48 that do match. And so, of course, the 48 is a longer match. All right, so how do we build a routing table? So the three major types of routes that we have in a routing table are directly connected networks. And so they're added to the routing table when a local interface is configured with an IP address and subnet mask and is active. So in other words, its status is up. And so they will be added automatically as soon as that interface is working. So remote networks are not directly connected to that router, and so routers learn about those remote networks either by static routes, and so someone has to type those in, and then but that's not all that has to happen for them to be in the routing table. Also, the next hop. You know, when you type in a static route, you tell it the destination network, you tell it the destination subnet mask. You also give it instructions on how to get it there. So you either tell it an exit interface or you tell it a next hop IP address. And so that exit interface needs to be up, or the router needs to know how to find that next hop interface, that next hop address. And so that needs to be true as well before a static route will appear in the table. And then with dynamic routing protocols, basically that's when that router and other routers are using the same routing protocol and they're exchanging information. And that's what they mean by dynamic. And so we've spoken about directly connected and remote networks. And so a default route is basically, it's a next hop router to use when the routing table does not contain a specific route that matches the destination IP address. The default route can be entered manually as a static route or learned automatically from a dynamic routing protocol. So when you see a default route in the routing table, it will actually have a /0 prefix length. This means that no bits need to match that destination IP address for this route to be used. And so you also may see the term of gateway of last resort. So in other words, if I don't have a good route for it, I'll use this one. So, you know, it's a fallback option. So if there are no routes with a match longer than 0 bits, the default route is used to forward the packet. The default route is sometimes, as I said, referred to as a gateway of last resort. So we were talking on previous slides, the longest match is the best match. Well, a default route is the shortest possible match. There's no bits that match. It's a terrible match, but hey, it might be the only match you have. All right, packet forwarding. So, of course, the process that happens with the packet forwarding and decisions for forwarding packets. So the data link frame with an encapsulated IP packet arrives at the incoming interface or ingress interface. The router examines the destination IP address in the packet header and consults its IP routing table. The router finds the longest matching prefix in the routing table. And then from there, of course, it uses the forwarding information in that entry to actually then decide where it needs to go. The router encapsulates the packet into another data link frame and forwards it out the egress interface. The destination could be a device connected to the network or a next hop router. However, if there is no matching route entry, the packet is dropped. And so if you don't have a default route and you've got a packet that we don't have a match for in the routing table, that packet will be dropped. There may be an ICMP message that gets sent back saying, you know, destination unreachable, but that's about all that will happen. And IP doesn't lose any sleep over it. So after a router has determined the best path, it could do the following. Forward the packet to a device on a directly connected network. And so if the route entry indicates that the egress interface is a directly connected network, the packet can be forwarded directly to the destination device. Typically, this is an Ethernet LAN. So in other words, you're saying the router we're talking about at the moment is the last hop towards the destination, and that router will send it to the actual destination host. So to encapsulate the packet in Ethernet frame, the router needs to determine the destination MAC address associated with the destination IP address of the packet. The process varies based on whether it's IPv4 or IPv6. So there's ARP, of course, for IPv4, or there's neighbour solicitation if it's IPv6. Similar process though. After the router has determined the best path, it could do the following. It could forward it to a next hop router. So if the route entry indicates that the destination IP address is on a remote network, meaning a device on the network that is not directly connected, the packet must be forwarded to the next hop router. The next hop address is indicated in the route entry. If the forwarding router and next hop router are on the Ethernet network, a similar process, either ARP or neighbour discovery, will need to occur for determining the destination MAC address as we spoke about. The difference is that the router will search for the IP address of the next hop router in its ARP table or neighbour cache instead of the destination IP address of the packet. This process will vary for other types of layer 2 networks. So ARP is only required on LAN networks. It's not required on point-to-point networks. Of course, the other option is I have no route entry, I have no match, and so you will drop the packet. So if there is no match between the destination IP address and a prefix in the routing table, and if there is no default route, the packet will be dropped. So the primary responsibility of the packet forwarding function is to encapsulate packets in the appropriate data link frame type for the outgoing interface. For example, the data link format for a serial link could be point-to-point, could be HDLC, or it could be some other layer 2 protocol. So of course it needs to know what encapsulation to use. So when a router does its forwarding function, it's actually got different options on how it will do it. So the primary responsibility of a packet forwarding function is to encapsulate packets in the appropriate data link frame of the outgoing interface. The more efficiently a router can perform this task, the faster packets can be forwarded by the router. And so there's 3 packet forwarding mechanisms available in Cisco routers. One is process switching. So what that means is the packet arrives, it's error checked as it arrives, and then it's actually put in a RAM, and the CPU processes it, and then it forwards it out, and it goes to that exit interface. And so that's an old traditional way of doing it. It's not a quick way of doing it though. So that's the slowest of these 3 options. Now fast switching is basically the first packet in a conversation will go through that process switching that I just mentioned about going into RAM and the CPU doing it, but it gets a little smarter in that it will also update a specialized forwarding table in hardware so that any subsequent packets in that conversation can actually be switched straight through hardware without the CPU and RAM being involved. So they call that fast switching. And then there's Ceph, which is Cisco Express Forwarding. And so instead of waiting for that first packet to happen to update this high-speed table, with Cisco Express Forwarding, it actually searches through the routing table and actually creates the entries before any packets arrive. And so with Ceph, it basically rarely will go through the process switching process. All right, so I've already explained what these slides say. An older packet forwarding mechanism is still available for Cisco routers. When a packet arrives in the interface, it is forwarded to the control plane where the CPU matches the destination address when they enter its routing table and then determines the exit interface and forwards the packet. It's important to understand that the router does this for every packet, even if the destination is the same for a stream of packets. So it's not a quick way to go. It's thorough, I suppose, but it's, yeah, slower. And so, as I said, fast switching uses the same process for the first packet, but while it's doing that, it also updates that fast forward cache, and then all the subsequent packets will actually go through an express process. And so basically that cache is just an information about what conversations are going on, and then it will actually expedite those packets through the router a lot quicker. And so, as I said, with Ceph, it basically reads the routing table, interprets it, and actually makes rules called a forwarding information base, an adjacency table, and it basically means that everything can be fast switched. Okay, so a review of router configuration. We have done this not all that long ago, but anyway. So here we've got a topology with 3 routers, router 1, router 2, and an ISP. We've got 2 LANs hanging off of each of the router 1 and router 2. We've got IPv4 and IPv6 addressing. And the reason why we've got the ISP there is that I'm assuming would be for a default route to the ISP. Okay, so of course we've got all their passwords and host names and other such things like that. And of course banner mopd messages as well are always good. And then of course we've got to configure addressing. Now I think I've mentioned this before. To get a Cisco router to play with IPv6 as a router, IPv6 unicast routing needs to be done to turn IPv6 routing on. You don't need to have that on to put the IPv6 addresses in, but without it, it's just a host. As soon as you turn that IPv6 unicast routing on, it actually becomes an IPv6 router. Okay, so how do we verify that we've got it all working? So show IP interface brief, that's always a quick way to get the IP addressing checked. Show running config, of course, is useful. Show interfaces, show IP interface, and so on. So show IP route, certainly good information. And of course, ping for a connectivity test is always good as well. All right, now you can actually filter output. Now, I don't think this filtering works very well, if at all, on Packet Tracer. That's the downside. Works nicely on the hardware, not so much on the software. But anyway, filtering commands can be used to display specific output, the sections of output. To enable filtering command, you need to use the pipe character. So it's either the 1 straight line or it's 2 straight lines. It's the uppercase of the / character on the keyboard, typically. And so you can actually say things like include, exclude, begin, or section. And so basically, output filters can be used in combination with any show command, as long as you've got the right options. And so basically, you can just have a look at the section or include output lines that match it, and so on and so forth. So it is very nice, but not, as I said, as far as I'm aware, it doesn't work on Packet Tracer unless version 8 has made it happen, but I haven't noticed it yet. All right, so routing sources. So a routing table contains a list of routes to known networks, prefixes and prefix lengths. The source of this information is derived either being directly connected, static routes, or dynamic routing protocols. Now, when you look at the routing table, there is actually the first character tells you where that route came from. And so L identifies the address assigned to the local router interface. C means the directly connected network. S means static. Some other letter normally means a routing protocol. And a star means that this route is a candidate to be a default route. Now, routing table principles. There are 3 routing table principles as described in this table. These are issues that are addressed by the proper configuration of dynamic routing protocols or static routes on all routers between the source and destination devices. Every router makes its decision alone based on the information it has in its own routing table. And so, just because router 1 knows how to find a destination doesn't mean router 2 knows. And of course, every router between source and destination needs to know that information to be able to forward packets. The information in a routing table of one router does not necessarily match the routing table of another router. Now, even if all the routers know everything, their routing tables will not be identical because every router is in a different position on the network. And so they won't have identical information. They will often have similar information, but But yeah, it doesn't. Then rarely, if ever, the same information. So routing information about a path does not provide return information. So just because your router can find the destination doesn't mean the destination can find you. And I think I might have actually demonstrated that once or twice, but anyway. And so basically every router needs to know pretty much everything for packets to be able to connect universally. So if router 1 receives a packet with a destination IP address of PC1 and the source IP address of PC3, just because router 1 knows how to forward the packet as G000 interface does not necessarily mean that it knows how to forward packets originating from PC1 back to the remote network of PC3. Okay, so routing table entries. And so as I said, the first thing on a routing table entry is actually the source of that information. And so here we've got an O, which means OSPF. So the routing protocol supplied this information. The next part of information is actually the destination network and its prefix length. And so here we've got a route to network 10.0.40 with a /24 mask. Now, of course, that's the same information here, but of course it's an IPv6 address. Okay, the next piece of information is actually the administrative distance. Now, the administrative distance is basically a tiebreaker between different routing sources. Now, on this one router, you may have a routing protocol. You may have static routes, you might have default routes, you might have and of course you're going to have directly connected networks. Now, if you've got information about a network from more than one source, you need to pick one. And so that's why they call it trustworthiness. So basically, what is the more reliable source of information? So if you've got a route from OSPF and you've got a route from RIP, two different routing protocols, Cisco at least will determine that OSPF is the more reliable routing protocol, so it will actually take its information. Now, directly connected networks, well, hey, if you're directly connected to a network, that's pretty much as reliable as you can get. And so that will actually have an administrative distance of 0, which is the lower the number, the better the admin distance. While OSPF, I think, has an admin distance of 110. Oh, of course, it's right here, admin distance 110. RIP actually has an admin distance of 120, and that's why OSPF is deemed to be better than RIP. So that's basically, if you get the same route from two different sources, you need to have a tiebreaker. And so the lower number, the more reliable. Okay, the next number is actually the metric. And so that is how far away is that destination. And that's actually, there may well be more than one route to that destination within OSPF. And so the shortest route is the best route. I'm going to say, would you rather drive to Victor Harbour via Mount Compass from here, or would you rather drive to it via, I don't know, Tailem Bend? You can do it, but Tailem Bend is going to be at least twice as far. And so that's the kind of thing. And so the shorter the metric, or the lower the metric, the better, again. All right, now we have next hop information. So, of course, to find this network, we need to go via this next hop. That's basically what it's saying. So again, here, that's what this is doing as well. It's just that it's the linked local address of the next router on the route. And then this last thing here is the exit interface. And so this is the interface you need to send it out of to get it towards its destination. And so serial 011. Note, the prefix length of the destination network specifies the minimum number of far left bits that must match between the IP address of the packet and the destination network for this route to be used. So again, we're talking about length of match. All right, so directly connected networks. So remote to learn about any remote networks, the router must have at least one active interface configured with an IP address and a subnet mask or prefix link. This is known as a directly connected network or a directly connected route. Routers add a directly connected route to its routing table when an interface is configured with an IP address and is up. Directly connected network is denoted by the status code of C in the routing table, and the route contains a network prefix and a prefix length. The routing table also contains a local route for each of its directly connected networks, indicated by an L. For IPv4 local routes, the prefix length is /32. For IPv6, the length is 128. So that denotes that it's actually a host address, it's not a network address. So this means the destination IP address of the packet must match all of the bits in the local route for this route to be a match. The purpose of the local route is to efficiently determine when a received packet from an interface receives it. So when it receives a packet for the interface instead of the packet that needs to be forwarded. So in other words, is it for itself or is it for a host on that network? All right, so static routes. So after the directly connected networks are added to the routing table, static or dynamic routing can be implemented for accessing remote networks. Static routes are manually configured. They define an explicit path between two networking devices. They are not automatically updated and must be manually reconfigured if the network topology changes. So static routing has three primary uses. It provides ease of routing table maintenance in smaller networks that are not expected to grow significantly. It uses a single default route to represent a path to any network that does not have a more specific route or match in the routing table. Default routes are used to send traffic to any destination beyond the next upstream router. It routes to and from stub networks. A stub network is a network accessed by a single route, and the router has only one neighbour. Okay, so how do we do a static route? So the command is IP route for IPv4, and it's IPv6 route for IPv6. And then you specify the destination network. So again, in IPv6, you specify the destination network. With IPv4, you supply subnet mask. You do a prefix length in IPv6. And then you need to give it the forwarding information. And so it's either the next top IP address or an exit interface. And so again here, next top IP address or exit interface. Now, dynamic routing protocols are used by routers to automatically share information about the reachability and status of remote networks. Dynamic routing protocols perform several activities, including network discovery and maintaining routing tables. Now, so OSPF is now being used in our sample topology to dynamically learn all of the networks connected to R1 and R2. The routing table entries use the status code of O to indicate the route was learned by the OSPF routing protocol. Both entries also include the IP address of the next top router by IP address. Note, IPv6 routing protocols use the linked local address of the next top router. OSPF routing configuration for IPv4 and v6 is beyond the scope of this course. So we actually do OSPF in subsequent subjects. Okay, so as you can see here, we have routing table entries. And so here we have O, as in OSPF, is the source of the information. We have the destination network, its mask, then it's admin distance, then it's metric, and then next hop IP address. One thing I didn't talk about in the previous slide was how long it will take for this network, without updates, to expire. So in other words, if I don't hear from that other router within 24 seconds, I will remove this route from the table. That's what that means. And then here, of course, is the exit interface. So here, of course, this is the routing table for IPv6. And so pretty much the same, except of course they're IPv6 addresses. And so destination network, prefix, admin distance, metric, next hop IP address, exit interface. Now, a default route specifies the next hop router to use when the routing table does not contain a specific route that matches the destination IP address. Default route can be either a static route or a learned automatically from a dynamic routing protocol. A default route has an IPv4 route entry of quad 0/0, or an IPv6, it's ::/0. This means that 0 or no bits need to match between the destination IP address and the default route. So much the same as my computer's been talking to Cisco's website today. TAFE-SA does not have routing entries for Cisco. It would be using the default route that it uses via its network provider. And so the network provider would need to know how to find Cisco, but TAFE-SA would not. Now here we have R2 is hooked into the ISP. So typically what you would do is you would type in that default route in R2. You could also type in a default in R1 and say R2 is our default route because, well, everything has to go through R2 to get to the ISP. Or another option could be is you do the default route in R2 and then you use your routing protocol to advertise that default route to the other router or all routers. And that's often a more efficient one. This is a pretty small network, so it's pretty much a toss-up with which is more efficient. Now, the structure of an IPv4 routing table. IPv4 was standardized using the now obsolete classful addressing architecture. The IPv4 routing table is organized using the same classful structure, although the lookup process no longer uses classes. The structure of IPv4 routing table still is retained in this format. An indented entry is known as a child route. A route entry is indented if it is a subnet of a classful address, so A, B, or C class. Directly connected networks will always be indented, child routes, because the local address of the interface is always entered as /32. The child route will include the route source and all the forwarding information such as next hop address. The classful network address of this subnet will be shown above the route entry, less indented and without a source code. That route is known as a parent route. Now, hopefully we've got a routing table here. Yes. So you can see here that this here is the classful entry, and it's a parent entry. And then we have this directly connected child route, and then we have the local link child route. And so here, of course, we have another parent route, and then we have child routes and so on. Now, an indented entry is known as a child route. A route entry is indented if it is a subnet of a classful address. Directly connected networks will always be indented child routes because of the local address. The child route will include route source and all information. The classful network address of this subnet will be shown above the route entry, less indented and without a source code. That route is known as a parent route. That seems like pretty much a repeat of the previous one, but anyway, it is. All right, structure of the IPv6 routing table. Because there is no classful addressing of any type, I think they're just basically done in numerical order. So the structure of IPv6 routing table is very straightforward. Every IPv6 route entry is formatted and aligned the same way. So there's no such thing as a parent or child route in IPv6. Okay, so administrative distance, I think I have already explained it. Now, a route entry for a specific network address, prefix or prefix length, can only appear once in the routing table. However, it is possible that the routing table learns about the same network address from more than one routing source. Except for very specific circumstances, only one dynamic routing protocol should be implemented on a router. Each routing protocol may decide on a different path to reach the destination based on the metric of that routing protocol. So, of course, this raises questions and problems. How does the router know which source to use? Which route should it install on the routing table? And so basically, comparing a route from RIP to a route from OSPF, you can't actually compare them directly because RIP uses one metric, OSPF uses a completely different metric. So you just can't compare metrics. They don't really compare. And so that's how you need to compare the protocols themselves. And so, as I said, it's the trustworthiness is what admin distance measures. And as I said, OSPF is more trustworthy, and I agree with that completely. I would pick information from OSPF before RIP anytime. Now, this is a table of a variety of administrative distances you can use, and what is used. And so directly connected networks are 0. As I said, if you're directly connected to a network, you can't get any more reliable than that, can you? Now, a static route is 1. And so if you type in a static route, it assumes you know what you're doing. Whether that's a good assumption or a bad assumption, well, that's open to interpretation. But it assumes you know what you're doing. And so it gives it an admin distance of 1. So if you've got a static route, and you've got a dynamic route, it will actually take the static route normally. You can change that. Now, EIGRP, well, don't worry too much about that. So EIGRP is actually a Cisco proprietary routing protocol. BGP is actually what's used on the internet. And so EIGRP normally has an admin distance of 90. That's what most of the routes will be. Summary routes are treated separately. As I said, OSPF is 110. The old version of EIGRP was called IGRP. E stands for enhanced. And that had an administrative distance of 100. And I must admit, I would actually personally put OSPF as being more reliable than both of those. But hey, it's Cisco. ISIS is another routing protocol. It's actually Open Standards Base 1. That's got 115, and RIP is 120, and so on. Now, these are the default settings for those admin distances. You can actually modify that. All right, static and dynamic routing. I think we're getting towards the end now, thankfully. Static and dynamic routing are not mutually exclusive. Rather, most networks use a combination of both. Static routes are commonly used in the following scenarios. To create a static default route, you need to have at least one static entry. For routes outside the routing domain not learned by dynamic routing, you might want to put in a specific static route. When the network administrator wants to explicitly define the path for a specific network, and for routing between stub networks. Static routes are useful for smaller networks with only one path to the outside world. They also provide security in a large network for certain types of traffic or links to other networks that need more control. So dynamic routing protocols are implemented in any type of network consisting of more than just a few routers. Dynamic routing protocols are scalable and automatically determine better routes if there is a change in the topology. So they're normally used in the following scenarios. Networks consisting of more than just a few routers. When a change in network topology requires the network to automatically determine another path, and for scalability. As the network grows, the dynamic routing protocol automatically learns about new networks. If you start growing a network with static routes, you've actually got to go back and configure every router in your network, which doesn't sound like fun. All right, so comparing the two, so what configuration complexity is there? And so dynamic routing is always pretty much the same no matter what the size of the network. Static routing, basically, as you add networks, the number of static routes that you need to add actually grows exponentially. And so after a while, static routing just becomes a nightmare. All right, topology changes. Routing protocols handle that automatically. If a network is down, the routers will actually tell each other, sorry, that network's now invalid. While in static routing, you have to go down and cancel all those routes yourself. That's not good. Scalability. So certainly dynamic wins that. Security. You can do security on routing protocols, but it's not default. While with static routing, because no traffic is running over the network, exchanging routes, it is actually secure by default. So resource usage, well, you will use resources like CPU, memory, and bandwidth to do all the exchanges and also all the calculations. Now, if you need path predictability, static routing wins that, but it's not often that you actually need that. All right, so dynamic routing protocol evolution. So it's been around for ages. So one of the first routing protocols is RIP. So RIP version 1 was released in 1988. It's before I was routing. But some of the basic algorithms within the protocol were used by ARPA, which of course is the Defense Research Agency for the US military, as early as 1969. As networks evolved and became more complex, new routing protocols emerged. Now, so basically, IGRP, RIP, ISIS, OSPF version 2, and so on, have all sort of come out. RIP version 2 is certainly the better one. RIP-NG is actually RIP version 2, but for IPv6. Now, BGP is what's used on the internet. Multi-protocol means that it also supports IPv6. And OSPF version 3, again, supports IPv6. Took them a while to bring out ISIS for IPv6, apparently. All right, now, there are several ways you can classify routing protocols, and this table sort of helps you with that. Now, the table classifies current routing protocols. Interior gateway protocols are routing protocols used to exchange information within a routing domain within a company, so administered by a single organisation. There is only one external gateway protocol, and that's BGP. Border Gateway Protocol stands for. BGP is used to exchange routing information between different organisations known as autonomous systems. And ISPs use BGP on the internet. Distance vector, link state, and path vectoring routing protocols refer to the type of routing algorithm used to determine the best path. Now, path vector is BGP, and basically it actually tracks every autonomous system that a router's gone through, and that's actually how it figures out if there's a routing loop. If it sees the same autonomous system number twice, it will actually ignore that route. Now, distance vector basically means it knows how far away the destination is, and it knows the exit interface, but that's all it knows. And so they're sometimes called distance vector routing by rumour, but anyway. So it doesn't sound good, does it? And so RIP version 2 and RIP-NG work exactly the same way, just one's for IPv4 and one's for IPv6. EIGRP, now I told you before, that's a Cisco proprietary protocol. It's actually pretty good. And but Cisco's actually stopped putting it in their curriculum now, other than the odd brief mention. But yeah, it's a pretty good routing protocol. I've got to give them that. Now, so and also Cisco used to call EIGRP a hybrid protocol, bit link state, bit distance vector. Now I think they call it an advanced distance vector. But anyway, it's all just naming. Now OSPF, you will do that if you carry on to do all of the networking stream. And so it's open shortest path first is what that stands for. And it's open, not in as in open the door, but open as in open source. And so version 2 is what we use on IPv4, and in version 3 is what we use in IPv6. Now, ISIS stands for intermediate system to intermediate system. And so that's what ISIS stands for, and there is one for IPv4 and there's one for IPv6 again. Now, a routing protocol is a set of processes, algorithms, and messages that are used to exchange routing information and populate the routing table with the choice of best paths. The purpose of dynamic routing protocols includes the following: discovery of remote networks, maintaining up-to-date routing information, choosing the best path to destination networks, ability to find a new best path if the current path is no longer available. Okay, the main components of a dynamic routing protocol are the data structures. So routing protocols typically use tables or databases for the operations. This information is kept in RAM. So the messages themselves, and so of course they use various types of messages to discover neighbouring routers, exchange routing information, and other tasks to learn and maintain accurate information about the network. And then there's the algorithm. So once you've discovered all the information network from your neighbours, you then need to figure out what's the best way to each destination. And that's the algorithm that does that. And so it's a finite list of steps used to accomplish a task. Routing protocols use algorithms for facilitating routing information for the best path determination. So routing protocols determine the best path or route to each network. That route is then offered to the routing table. The route will be installed in the routing table if there is not another routing source with a lower administrative distance. Okay, so the best path is selected by a routing protocol based on the value or metric it uses to determine the distance to reach a network. The metric is the quantitative value used to measure the distance to a given network. The best path to a network is the path with the lowest metric. Dynamic routing protocols typically use their own rules and metrics to build and update routing tables. The following table lists common dynamic routing protocols and their metrics. Now, RIP, of course, stands for Routing Information Protocol. It uses a metric of hop count. And so basically, when RIP is passing routes on, they just add one to the metric as they go. Now, because RIP is susceptible to routing loops, it actually has a maximum of 15 hops. So RIP only really works well on smaller networks. Now, OSPF uses a metric of cost. Now, that's calculated by the bandwidth. The higher the bandwidth of a link, the lower the metric for that link. And so cumulative, basically, you add up the cost for each link between the source and the destination, and that is your cost to get to it. Faster links are assigned a lower cost compared to slower links, which are, of course have higher costs. Now, EIGRP, it uses a combination of bandwidth and delay to calculate its metric, but it actually has an option to use load and reliability as well, except it's sort of discouraged. So that's actually why, I think that's why Cisco actually has EIGRP as being more trustworthy than OSPF, because it's got a more complex metric. I'm going to say it does certainly have a good metric, but you know, it's not the only thing you compare. Anyway, load balancing. When a router has two or more paths to a destination with equal cost metrics, then the router forwards packets using both paths equally. This is called equal cost load balancing. So the routing table contains a single destination network but has multiple exit interfaces, one for each equal cost path. The router forwards packets using the multiple exit interfaces listed in the routing table. If configured correctly, load balancing can increase the effectiveness and performance of the network. Equal cost load balancing is implemented automatically by dynamic routing protocols. It is enabled with static routes when there are multiple static routes to the same destination. Only EIGRP supports unequal cost load balancing, but you don't need to worry too much about that. Hallelujah. So, in summary, the primary functions of a router are to determine the best path to forward packets based on information in its routing table, to forward packets toward their destination. The best path in the routing table is also known as the longest match. The longest match is the route in the routing table that has the greatest number of far left matching bits with the destination IP address of the packet. Directly connected networks are networks that are configured on the active interfaces of a router. A directly connected network is added to the routing table when that interface is configured with an IP address and mask and is active. In other words, it's working. Routers learn about remote networks in two ways, either by static or dynamic routes. After a router determines the correct path, it can forward the packet on a directly connected network, or it can forward the packet to a next hop router, or if it doesn't know what to do with the packet, it will be dropped. Routers support three packet forwarding mechanisms: process switching, fast switching, and CEF, which is Cisco Express Forwarding. There are several configuration and verification commands for routers: show IP route, show IP interface brief, and show running config. Okay, a routing table contains a list of routes or known networks, so it's the prefix and prefix lengths. The source of this information is derived from either directly connected networks, static routes, or dynamic routing protocols. Every router makes its decision alone based on the information it has in its own routing table. The information in a routing table of one router does not necessarily match the routing table of another router. Routing information about path does not provide return routing information. Routing table entries include the route source, destination network, admin distance, metric, next hop, route timestamp, and exit interface. Static routes are manually configured and define an explicit path between the two networking devices. Dynamic routing protocols can discover a network, maintain routing tables, select the best path, and automatically discover a new best path if the topology changes. The default route specifies a next hop router to use when the routing table does not contain a specific route that matches the destination IP address. Default route can either be static route or learned automatically from a dynamic routing protocol. IPv4 routing tables still have a structure based on classful addressing represented by levels of indentation. IPv6 tables do not use the same structure as IPv4 ones. Cisco OS uses what's known as administrative distance to determine the route to install in the routing table. The admin distance represents the trustworthiness of the route. The lower the AD, the more trustworthy that source. Static routes are commonly used as a default route, forwarding packets to a service provider for routes outside the routing domain and not learned by the dynamic routing protocol. When the network administrator wants to explicitly define the path for a specific network or for routing between stub networks. Dynamic routing protocols are commonly used in networks consisting of more than just a few routers. When a change in network topology requires a network to automatically determine another path and for scalability. As networks grow, the dynamic routing protocol automatically learns about any new networks. Current routing protocols include interior gateway protocols, exterior gateway protocols. Interior gateway protocols exchange routing information within a routing domain administered by a single organisation. The only external gateway protocol is BGP, which is Border Gateway Protocol. It exchanges routing information between different organisations and is used by ISPs to route packets over the internet. Last slide. Distance vector, link state, and path vector routing protocols refer to the type of routing algorithm used to determine the best path. The main components of dynamic routing protocols are data structures, routing protocol messages, and algorithms. The best path is selected by a routing protocol based on the value or metric it uses to determine the distance to reach a network. The best path to a network is the path with the lowest metric. When a router has two or more paths to a destination with equal cost metrics, then the router forwards the packets using both paths equally. This is called equal cost load balancing. There's the logo. Hallelujah. So that's the end of chapter 14. And that will do us for the day. We'll see you later.